Hello, so today we will look into the task that our teams had on 8th of October. So the task is to find the number of ornaments of a given length. What is the ornament? So the ornament is some sequence of letters of the letters that are used in Roman numerals in such a way that this is valid non-Roman numeral, this is valid Roman numeral. So all pairs of consequently written letters are valid Roman numerals, but three of them are not. Any three of them are not valid. So we need to find the number of such sequences. That's the whole question. So we look at the examples they give us. So they told us that for 2 there are 31 such sequences. What does it mean? You cannot build 3 that are not valid if there are only 2 letters. It's just an example. So for 1, 2, and 3, you must answer with so 1 is invalid. You cannot. For 2 and 3, you will give these sample answers. And for anything else above that number, we will just show you how to do this. So what we do, imagine that we build every single sequence that is ornament for 3 or length of 3. So all 28 sequences we already have. Such an example will be this number or this number. Why? Because this is 2, this is 4, but this is invalid number. You cannot deduct 2 from 5. Only 1 can be deducted. The same goes with that. So there are some of these sequences. We have 28 of them. And for the sequence that is written as A, B, C, we will construct a matrix. So what we do, we list all A, B. Then we list all B, C that are not listed yet. If there are no such BCs, we list them as well. Then we have, this is the rows, and then we have columns. So this will be our matrix. And what do we do here? So for ABC, ABC is in the list. Then we put here 1. And if there is no, so it's impossible to have ABAB, as we said that this letter must be the same as this letter. So as this is impossible, we write 0. F, so we can have like ABF, but ABF not in the list. ABF not in the list of all ornaments of length 3. Then we also write here 0. So we fill our matrix with such numbers. So what is the question now? The question is, what does it give us? The total sum of all numbers in this matrix is 28. So it is the number of ornaments of length 3. Let's say that this matrix is matrix K. Now we need to find how many ornaments of length n there are. So we just use our matrix K and raise it to the power n minus 2. So for n equals 3, we have 3 minus 2 is 1. It will be just K. For n equals 4, we will have 4 minus 2 is 2. So we need to find K squared. On this point, the complexity is linear, but we do not raise anything to any power like that. We don't use linear algorithm. We use logarithmic algorithm. So it will be 2 times logarithm n times the number of rows. So we have some rows in matrix K squared. So it's enough. So how do we raise to the power using that? Imagine that n minus 2 is some number written in Boolean form, binary form. So what we do next, we start with the smallest number. We put W as K, then answer as identity matrix. Then we start going in the loop. So from here to here. So if this bit equals 1, then answer is multiplied by W. In both cases, the next value of W is W squared. So as you see, we only use the logarithm of operations, as it is the length of this number in binary notation. So the answer will be our answering matrix. Then we find the total sum of all numbers in this matrix, and it will be the answer to this question, to the task. So why is the total sum in the answer? So what does our matrix mean? So this matrix means how many paths from AB to BC, from any vertex to any other vertex of length 1 there are. If we raise this matrix to any power, for example to power t, then it means that there are so many paths from any vertex to other vertex of length exactly t. So this is how it works. That's all.